Hello everyone, can you hear me? Hello, can you hear me? Anyone? We will wait for a few minutes more for others to join and then we will start at 7:10. Hello everyone. Can you hear me? Anyone?
Yes, sir.
And my screen is visible. I have shared the slides.
Yes, sir.
Okay, thank you. So I welcome you all again to the interaction session on the NPTEL course Experimental Physics, which is being flowed this July 2023 session. Myself, Vivekananda Nayak, I am a Prime Minister Research Fellowship holder, research scholar in the Department of Energy Science and Engineering, IIT Delhi. So in last week, we discussed about like multimeter, how the galvanometer is being converted to voltmeter, how it is being converted to ammeter, then cathode ray oscilloscope, the operating principles of cathode ray tube, how the electrons are getting deflected with the help of electric and electric fields, so that we can identify the spot varying on the screen, and how the device is used to take different measurements. So while we are performing the experiment, there are some basic analysis which we need to know that was covered in the week 3 and week 4 lectures of the course. So it includes data collection, that is how we when we are performing an experiment, we need to first note down the data or collect the data from the experiment. So how to collect the data, that is to which factors we should look into when we are performing an experiment, so that we can collect the data effectively. Then after collecting the data, we will be using graph to plot the data, because most of the cases you are doing experiment to find the dependence of some quantity on other quantity. So only by means of graph we can know whether the quantity is varying linearly or decreasing, increasing, like that. Then calibration, the instrument we are using, whether this instrument is calibrated or not, we will be discussing it in details in the upcoming times. And then error analysis, like the data we have measured or calculated, whether there is some error, how to calculate the error and how to identify those error, and what are the source of error also we will discuss in today's session. So first, let us discuss the data collection. Now when we talk about data collection, there are different things that we should keep in mind, like repeat the measurement and take average. Generally, when we do experiment, we try to do experiment several times, so that we can minimize the error. Because when suppose we need to calculate suppose we are performing an experiment with a simple pendulum, and we need to calculate the time period of oscillation of the pendulum. So when we are calculating the time period, it might be the case that in first attempt when we are calculating, there was some time lag between the starting time of the oscillation and the person who was using the stopwatch. So there was some delay in the working of the stopwatch, so there are some errors. So when you are trying to do the experiment several times, that is when we are repeating the measurements, then we can minimize the error. Suppose for example, if we are trying to measure the width or height of a object, then in one reading there might be some error. But when we are taking the several measurements and those readings are very close to each other and they are varying a little bit, then when we are taking the average of that number, then we can minimize the error. Similarly, when we are plotting the graphs, like choose appropriate steps of x variable and note down the y variable. Like when we are performing an experiment, there are two variables. Suppose we are changing some variable, and with respect to that variable, this variable has to effect with some other, so that another variable is changing. So we should appropriate choose the steps. Like for example, when we are when we are measuring the voltage or current relation across a resistance, then the resistance is constant, so current will be directly proportional to voltage. So since here the relation is linear, so we can go stepwise. Like if we are increasing I, then V will increase linearly. But when there are quadratic relations, then we need to find, for example, this is X and Y. Suppose when we are at X equal to 0, Y equal to 0, at X equal to 5, Y equal to 25, then at X equal to 10, Y equal to 105. like that. So in this way, when we are seeing that the variable is changing much, then we have to decide the ranges of that variable. For example, if we want to calculate the output in same step, so we will take like x and y. Suppose x equal to 0, y equal to 0. For y equal to 5, we will take x equal to 1 or 2. For y equal to 10, then x equal to 1.5 or so, like that. So we will be choosing the appropriate step for x and y, which will be better for us when we are plotting the graph. Because when we are plotting the graph, then we need to identify those points. And if we are not recording the graphs in accurate steps, then it will be difficult for us to plot the graph and to replicate the points in the graph. Then take optimum quantity of substance or parameter. So when we are, for example, when suppose you want to calculate the density of a water, then what we will do, we will first measure the, we will first take some water with some volume, then we will weight, then we will measure its mass, and then according to the formula, that is density is equal to mass by volume, we will calculate the density. So for example, we are measuring 100 ml of, we want to measure the density of water. Suppose the measuring beaker we are taking is of 100 ml. Then what amount of water should we take so that we will be performing experiment? If we are taking 5 ml, then suppose you are taking 5 ml, then there will be some error, because the minimum, if you are taking a 100 ml cup, the minimum calibration or minimum mark of it is suppose 5 ml. So when you are taking 5 ml, there must be some error. And also when you are measuring the weight, then the weight will be very small. The weight will not be so significant. So in order to get the accurate result, we should take optimum quantity. For example, if we are taking 50 ml or 75 ml, like that, then the mass of 75 ml of water will definitely be much more. So using the weight measuring machine, we can effectively measure the amount of mass. So we should take optimum quantity of substance while performing the experiment, because it also again depends upon the least count of the instrument. Because suppose we are measuring the mass of the water and we are taking 5 ml of mass, but the measuring instrument we are using to measure the mass, the least count of that instrument is suppose 10 gram or 12 gram. Then when we are taking 5 ml of mass, 5 ml of water will be having less mass, that is lower than 10 or 12 gram. Then in that case, the measurement is not accurate. So there will be error in measurement. So in order to reduce the error in the measurement, we should take optimum quantity so that it will be easier for us to calculate the values. Then choose the instrument of smallest lead count when x and y have non-linear relations. Because when we are using some when we are performing experiment and the two quantities varying non-linearly. For example, x is y is varying, which is direct proportional to x to the power q. So when we are performing the measurements, suppose we are performing the suppose we are calculating volume, then volume will be, suppose we are calculating volume of a cube, then the volume of a cube will be length into the cube of the sides. Then when we are measuring the sides with a meter scale, suppose a small scale which are least count of only 1 mm, then we are measuring it 5.1 mm, then it will be 5.1 to the power 3, so that we will be calculating the volume of the cube. But when, if you find, suppose the accurate measurement is 5.12, then when we are taking 5.12, when we are calculating the cube of the 5.12, then it will be definitely different from that of the cube of 5.1. So when you are seeing that the relation between two variables are nonlinear, then the slight increase in one variable will reflect in the significant increase in the other variable. So in order to reduce that error, we need to use the instrument which will be having least count, so that the measurement will be accurate and there will be less error. So now we'll be solving a few problems which are based on the significant numbers, significant number of significant figures. You must remember these are the rules and the examples we had discussed in the fast interaction session also. But since we will be solving a few problems regarding these significant figures, then we should overlook the, or we should review again the rules that are used in significant numbers. So the rule 1 says all non-zero digits in a measurement are significant. So suppose we are taking some measurement or reading and there are all non-zero numbers. So all non-zero numbers are significant figures. However, some of them are doubtful of them and some are accurate. Suppose in a meter scale, if you remember, I had also discussed. Suppose in a meter scale, I am measuring an instrument and the least count of the meter scale is 1 millimeter. So when the size of the object is between suppose the size of the object is 2.12. So after measuring 2.1, we can't say whether it is 2.1 or 2.2. So it will be lying in between. So between that, suppose the measurement value we took, it is 2.12. Then 2.1 is actual reading because the least count of the scale is 1 millimeter and this 2 is doubtful digit. However, all these three digits, since they are non-zero, they are all significant. So when we are taking all non-zero digits in a measurement, they are significant. And then all digits in the coefficient of a scientific notation are significant, but those digits in the base and power are not. So when you are writing this, suppose I will be writing 2.12 and I'll be writing it 0.212 into 10 to the power 1. Then here it will, you can see this 0 will not be significant, 2, 1, 2, 3 will be significant, and then this 10 and 10 to the power 1 will not be significant. So in 1.40, for example, in 1.40, there are only 3 significant figures, 1, 4, and 0. These 3 and these 10 are not significant. And in these figures, as you can see, there are 8 significant figures because 1, 2, 3, 4, 5, 6, 7, and this 8. So in a scientific, if some reading is written in scientific format, like some coefficient into 10 to the power something, then irrespective of all the whether they are 0 or non-zero, they are all significant. Like here, if we see here in this, there are 3 digits, there are the 8 digits, and all these 8 digits are significant. Zeros that appear between non-zero digits are significant. When like here 2 zeros are appearing between non-zero, they are significant. So it has all 5 significant figures and 5.02 has 3 significant figures because this 0 is lying between 5 and 2, which are non-zero. But however, the zeros that appear the final non-zero digit in a number with a written decimal points are significant regardless of whether the zeros appear before or after the decimal point. So in suppose like here we are saying if the number contains decimal number, then whether the 0 lies before or after the decimal number, they are significant. So when I'm writing in decimal, all zeros are significant as well as since non-zero is also significant generally. So in 620.0, these are 4 significant figures, and in 1940.00 has 6 significant figures because it contains decimal number. So it has 6 significant figures. But zeros that appear before the first non-zero digit in a number are called leading zeros. Leading zeros are non-significant. But here you can see the zeros that are appearing before a non-zero number, these are not significant. Here only one significant number is 8 and here also one significant number is 8. But when some non-zero numbers are present before 0, then if this is decimal number, then it has significant. So these two rules are quite similar, but we have to remember whether which one are significant, which are non-significant. And again, zeros that appear after final non-zero digit in a number are not significant. If the number has no decimal, here 620.0, it has 4 significant figures because it has decimal. But here 620, it has 2 significant figures, 6 and 2. And here 1940, since it has no decimal point or it is not a decimal number. So the significant figures in this case is 3, 1, 9, 4, and not 0 is not significant here. So these are some rules to identify the number of significant figures. So now let's solve a few problems. This problem says write the result of the following with respect to significant figures. So we need to find out what are the number of significant figures here and what are the number of significant figure here, and then the result will be having the significant number which is least of these two significant, because when we are calculating some result, the significant, the number of significant we can add in the result is the list of the different quantities that are being measured and the number of significant digits in them. So the question says write the result of the following with respect to significant figures. So we will add, so when we are adding 9.65 and 15.237, then what will be the answer with respect to the significant figures, and we have to consider what will be the number of significant figures in, because in these answers you can see there are different number of significant figures. So you need to identify which of them is correct. So I'll be giving you 1 or 2 minutes and then I will solve it. Yes, can anyone tell me in question number 24 what will be the answer? Anyone?
So 24.9.
Once again.
24.9. Sir, option D.
Okay, any other answer? Actually, the thing is, when you are adding 15 points, suppose you are adding 15.237 plus 9.65, it will be how much? It will be 24.887. 24.887. But when you see these two numbers, in this number, there are only two numbers after the decimal point, but here there are three numbers. So in our result, we will be taking only two significant figures after the decimal numbers. So here, since in this number 9.65, we have two significant numbers in the, if there are non-decimal numbers, then the rule is different. But when there are decimal numbers, after decimal numbers, there are, as you can see here, it has two numbers, 0.65, 6 and 5. So in the result, we'll reduce it to two numbers after decimal. So 87, we know if it is greater than 5, so we can write it 24.89. So 24.89 will be the answer, because in 9.65, the value is two digits after the decimal number. So the answer, so the result should be correct up to two decimal numbers. So after the decimal, we will be taking two numbers. So this 24.89 will be the correct answer. Similarly, if you are considering the next question, write the result of the following with respect to significant figures. And this is 7.897 minus 5.45. Then can anyone tell me what will be the answer?
2.54.
Sorry, once again, I could not hear you properly.
2.54.
Yes, the answer will be 2.54. Because when you subtract 7.987 minus 5.45, then the actual answer is 2.537. 7. But since in this 5.45 there are two numbers after decimal, so our answer should contain two number after decimal. So we can accurately define two numbers. So here, since this 37, it will be reduced to 2.54. Since this 7 is greater than 5, so this 37 will be converted into 2.54. So the correct answer is 2.54. Is that clear? So then next question, and this question says write the result of the following with respect to significant figures. So here the question is 4.372 into 11. So can anyone tell me what will be the result of this multiplication with respect to significant figures? 4.372 into 11.
Option B, sir.
48.092 you are saying.
Sir,
Please
option A.
Yes, it will be option A, 48. So we will solve it. After 1 or 2 minutes, let everyone try you also try the 27 number question. It also says write the result of the following with respect to significant figures. 210.1 divided by 5.5. So it is a division. The above one was multiplication. The below one is a division. So what will be the answer? I again request everyone, please mute themselves unless you are asking some doubt or telling the answer.
Option A, sir.
Yes, in 26, option A will be correct. That is only 48. It is 4.372 into 11. So the actual multiplication is 48.092. But since here 11, there are no numbers after the decimal, or it is a non-decimal number. So in case of non-decimal number, all these 1 and 1 both are significant. So our result should contain only two significant figures, because here it has 4 significant figures, but here it has 2 significant figures. So our result contains the least. So our result should contain 2 significant figures. So the result is rounded up to only 2 significant figures, and the correct answer will be 48. And then in question number 27, it is a division. So here when you see both are decimal numbers and they are being divided. So here in 2101, it has 4 significant figures, but here in 5.5, it has 2 significant figures. So when we are dividing it, then it will be how much? 210.1 divided by 5.5. So it will be 38.2. But since here only has 2 significant figures, 5.5 has 2 significant figures, so our result should be rounded up to only 2 significant figures. So the answer will be 38. So in question number 27, it will be 38, and in question number 26, it will be 48, because here 11 has only two significant figures, and here 5.5 has only two significant figures, because both are of decimal numbers and it contains least number of significant figures, and the least number of significant figures in this case is 2. So in 5.5 there are two significant figures, so our result should contain two significant figures. So these are a few things. These are a few problems related to significant figures. So we had also solved different a number of problems to identify the number of significance in the first introduction session. So now another question comes. The length, breadth, and thickness of a rectangular sheet of metal are 4.235 meter, 1.005 meter, and 2.01 centimeter respectively. Calculate the area of the sheet to correct significant figures. So you simply you have to calculate the area of the sheet, because it is a rectangular sheet and it contains length, breadth, thickness. So will be have to calculate. We'll be calculating all the 6 surfaces and their surface area. So calculate the total surface area of the rectangular sheet and tell me what will be the answer. And it is corrected to a number of significant figures. So as I have said previously, when you are having some input numbers or given numbers, then the result will be the number of significant figures in the result will be the least of the number of significant figures already provided. So we will be calculating the total area. Then we will be seeing the number of significant figures in each digit given, and then from that we will find the minimum number of significant figures, and that least number of significant figures, the answer will be having that number of significant figures.
Hello, sir.
Yes.
Sir, option A is correct.
Yes, good. Option A is correct. So anyone, why option A will be correct? Can you say me?
Yes, sir. Option A is correct.
Sir,
Why option A? Yes.
I have used the formula of surface area.
Yes.
2 in bracket length into breadth plus breadth into thickness plus thickness into length as well.
Yes.
And I am calculating, and in last Uh, I can see in the thickness there are three significant figures.
Yes, it's correct. So when we are calculating, so let's calculate it. So as you can see here, we have length, breadth and thickness. So length is given 4.234 meters. Breadth is 1.005 meter and thickness or height is 2.01 centimeter. So this 2.01 centimeter has three significant figures, but since we are calculating in meter square, so we need to convert all the given entities into meters. So it will be, so 1 meter is 100 centimeters. So it will be 0.0201 meter. But when you are calculating the number of significant figures, here the number of significant figure is 4. Here the number of significant figure is 4. But here the number of significant figure is 3. So the result should also contain the least number of significant figure, that is the answer should be significant up to 3 figures. So when you are calculating, suppose this is a cube, this is a rectangular sheet, suppose, not cube. So it has 6 surfaces. This surface, this type of 2 surfaces, and this type of 2 surface, and this type of 2 surface. So when you are calculating total surface area will be 2 into L into B plus B into H plus H into L. So when you put all the values and you calculate, since here we'll be multiplying 4.234 into 1.005, so the actual result will be, and here also after decimal there are 4 numbers, so the actual calculation will give us 7 numbers after the decimal point. So it will be 8 point, when you calculate it actually, that will be 8.7209 478 meter square. So this is the actual result of the multiplication. But since the question is given to calculate the area of the sheet to correct significant figures, so we have to consider the least number of significant figures in the given entities. So as you can see here, the least number of significant figures is 3. So when you are writing the answer, it will be correct up to 3 significant figures. When we are taking 3 significant figures, so first 3 digit we will be taking, so it will be 8.72 and the unit is meter square. So the correct answer will be 8.72 meter square. So let's try another question. Now again, this says the mass of a body is 263.2 grams and its volume is 24.2 centimeter cube. So calculate the density of the substance up to appropriate significant figures. So it will be, it is very similar to the previous questions. So calculate and tell me what will be the correct answer and what should be the number of significant figures in the result.
Option B, sir.
Yes. So why it will be option B?
Sir, because I have the mass formula, sir.
No, let me discuss. Actually, here we have 263.2 gram and volume is 24.2 centimeter cube. So we know density is given by mass by volume. So it will be 263.2 divided by 24.2. and it will be gram per centimeter cube. And when you calculate it, it will be how much? It will be 10.87, 10.87603306 in gram per centimeter cube. But since here you can see there are 4 number of significant figures and here there are 3 significant figures. So our result should contain 3 significant figures. So when we are reducing it to 3 significant figures, then it's 10 point, since it's after 8 it is 7 and 7 is greater than 5, so we will be taking 10.9. So the correct answer will be 10.9 gram per centimeter cube. So it will be 10.9 gram per centimeter cube. So this is the correct answer, and the density is 10.9 gram per centimeter cube. So now after data measurement, then we need to plot the graph. So we should know about how to plot the graph. So let's discuss about graph plotting. So there are different types of graphs. For example, one is line graph, and in line graph generally we use line graph to say to show some trend, like when you are seeing some quantities varying, reducing or increasing with respect to another quantity, then when you are when we are representing it in terms of line graph, then we can easily say whether the function is increasing or decreasing with respect to the variable. And then the next graph is bar graph, and as you can see, bar graph is generally used to compare the two variables. For example, if there are product A and B here, in 2015 the sales was 60,000 for product A, for 40,000 for product B. So these bar graphs or bar charts are used to show the difference or to show the comparison between two objects. And then you must be very acquainted with the pie charts. So pie charts basically show the portion or rational dependence. For example, in our atmosphere we have 100% out of 100% we have 78% nitrogen, 21% oxygen, like that. So like that we have this pie chart, and the total sum of this will be 100%. And in case of histogram is when you are now, as you can see here, there are discrete numbers like 2012, 2013, 2014, like that. But here, as you can see, there are ranges. So when you are separating the variables into different range, then in that range we need to do a value so that the things are continuous, like it is 25 to 34, then 35 to 44. So in this case, to represent the thing, we use histogram. So how to plot a graph? So there are different steps to plot a graph. So the first step is to identify the variable, that is we need to identify the two variables we will be plotting, so that x, and generally we plot graph in x and y. So we should identify what we will be taking in the x-axis and what we will be taking in the y-axis. Then in step 2, determine the variable range. So you must remember when we plot graph, there are small squares in the graph, like that. This is a graph paper. There are small squares. So when we plot a graph, we define this one scale to some unit. So that decision we will be taking, that is the that decision will be depending upon the range of the variable. So suppose we are taking x and y, but x is varying from 0 to 100, but y is varying from, suppose y is varying from 0 to 10. So, but when in the graph paper, there are 10 divisions, suppose. So in that case, since the range of y is 0 to 10, so y is varying 10, but x is varying to 100. So in that case, the range to make the graph to look a bit look familiar to us, we should assign the ranges or assign the scales different for both x and y. So for x and y, we will assign this one scale 1, 2, 3, 4 like that. But in case of x, we will assign 10, 20, 30, 40 so that within the given space, we can plot whole range of x and we can assign whole range of y to it. So we need to determine the variable and then we need to determine the scale of the graph. So this is about scaling. Then number and label each title the graph. So when you are suppose you are making in current and voltage, so we should voltage, we should write it voltage and we should write the unit. In current, whether it is milliampere or ampere, we should also write the unit. So we should number and label each axis, and also we should write the title of the graph. And then in order to plot the graph, we need to have the data points. So this part is very important. So how to determine those data points? In case of experiment, when you are getting the data point that are direct, we can input those data points in our graph and then we can plot a graph. But when we have to plot graph of some functions, then how we should plot the graph? And then after that, so this step will be very important. How to determine the data points? In case of experiment, it is simple, but when we are plotting different functions, like we will be plotting in some time. And then after that, in step 6, after assign the data point, suppose these are the graph, you assign the data point here, 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 and here, then you will plot the graph like so. You will draw the graph. So this graph is done. So, but when you are plotting the graphs of a function, then how to plot the graph of a function? So in case of function, we know in case of function, there is a variable. So the function of x, here the variable x, and we will suppose say y is equal to fx. So here x is variable and y depends upon the x. So we need to find the value of the function x. So when we need to plot the graph of a function, there are few things that are important and we should consider and keep in mind while plotting. The function fx, it will do, it will give the value of the function at the point x, and from that value we can say whether the value is negative. If the value is positive, then it will be lying in some quadrant, and whether the value is negative, it will be lying in different quadrant. So the values of x and y and whether they are positive or negative will determine the point, the position of the point in a particular quadrant. And then f prime x is the first derivative of fx with respect to x. It gives slope of the function, and we know when you take the first derivative of a function, it gives us slope, that is, it gives us the rate of change. If the slope is positive, then it is increasing, but if the slope is negative, then it is decreasing. So the slope of the function gives us whether the function is increasing or function is decreasing. Then f double prime x, and f double prime x means double derivative of f with respect to x, and gives us curvature. Curvature means whether the function is at some point of function, this increasing decreasing behavior changes. So whether the function has some maxima or minima, when the function was increasing and they suddenly start decreasing, then at that point the function has maxima. So this curvature, that is the double derivative of the function, will help us to find out whether it has maxima or minima at that point. That is whether it has concave or convex shape of the function. Like here you can see it is which shape? It is, there are two shapes. We can say it concave or convex, or we can say in other words we can say concave down and concave up. So in order to find this nature of the graph, we need to find the double derivative of the graph. And then when we are plotting a graph, we need to first find the x-intercept and y-intercept, then minima, maxima. So x-intercept, at x-intercept y equals to 0. So when we put y equal to 0 and solve for x, then that x will give us x-intercept. And for y-intercept, similarly, when the graph intersects at y-axis, then at that point x equal to 0. So when we put x equal to 0, then the value of y will be the y-intercept. So this x and y-intercept becomes important when we are plotting a graph, because it will say where the graph will cross x-axis or y-axis. When it crosses y-axis, it is y-intercept. When it crosses x-axis, it is x-intercept. And we know along y-axis, x is 0, and along x-axis, y is 0. So it will help us determine the point. And then another important point, another important property or another important thing is point of inflection. So basically, point of inflection is where the nature of the graph changes or concavity of the function changes. Like here you can see this function, this was concave down, but at this point it was concave up. So this curvature is changing sign. The curvature here, the curvature was positive, and but here the curvature negative, like that. So where the curvature changes sign, that is called as the point of inflection, and that point of inflection means the double derivative is equal to 0. If the double derivative is positive, it has concave or convex shape. Double negative, it has suppose double derivative is positive, it has concave up. Double derivative negative, it has concave down or convex. But when it is 0, then that point is called as point of inflection. And again, another is asymptote. And when you are plotting some graph, asymptote is important. And this asymptote, what is a asymptote is called? And asymptote is a tangent to a curve at infinity. That is, when you are drawing a graph and it tends to infinity, then at infinity, so generally we can say that the asymptote is a tangent to a curve at infinity. That is, at infinity, the function at which point the function tends to infinity. So that the asymptote and the curve will be tangent to each other at the infinity. So there are different types of asymptote. For example, horizontal asymptote and vertical asymptote. So as you can see here, for this curve, this asymptote at point C is vertical asymptote. But here, as you can see, these two will definitely meet at infinite only. But here, similarly, here it will definitely meet at infinite. So this at x equal to C, we can say x equal to C. This is the line. This is a vertical asymptote, and this is parallel to y-axis. And this similarly for horizontal asymptote, it is parallel to x-axis. That is y equals to v. This y equals to v is an asymptote parallel to x-axis. So this is a vertical asymptote and this is a horizontal asymptote. Also, asymptote can be inclined. So there are three different types of asymptotes. So now, when you are now let's take simple example. Now in this figure, you can see there are a number of graphs which are drawn in different colors. And as you can see here, the graphs have different slopes and different. So these graphs have different slopes. After a few minutes, we will see when they have different intercepts. So here, as you can see, this is fx equal to x. So here, when you compare it to, since this is a straight line, so when we write it in terms of equation of straight line, we know of straight line is y equals to mx plus c. So when you compare it, then m is equal to 1. So slope is 1. So since slope is 1, this will be how much? This will be 45 degree. But when we are saying fx equal to minus x, then for minus x, slope is minus 1. So it will be different. So here, the two graphs have different slopes. As you can see, I have circled it through thick red sign. So these two graphs, one is fx equal to x, another is fx equal to minus x. These are different slopes of different nature. But here the slope is positive, but here the slope is negative. So one is increasing in another direction, another is increasing in another direction. So again, if you here it is fx equal to 1 by 2x. So here slope is 1 by 2, but here slope is minus 1 by 2. So this is minus 1 by 2 and this is plus 1 by 2. So again, it is 1 by 3. So minus 1 by 3 is not given here. So similarly, you can say these graphs have different slopes. For fx is equal to 3x. So what slope says? Slope says the whether it increases or decreases, and also since slope is negative, it is decreasing. Slope is positive, it is increasing. And the rate of the slope, the value of the slope says how fast. Suppose the function here you can see this is 1 minute. So suppose we plot f y equal to x and y equal to 2x. So y equal to x will be this, but y equal to 2x will be this. So as you can see, this one is of 2x and this one is of x. So here the rate of increase is slow with respect to this, but because at this point, suppose x will be a, but here x will be b. Similarly, y will be suppose a prime, y will be b prime. So here definitely b is less than a, but the value of y at b is more than that the value of a. So here as you can see, since the slopes is changing, the rate of the function is changing, but the function is increasing rapidly due to the slope. Similarly, this is varying slope, this is varying the intercepts. So we have varied here x intercept. So as you can see, these are 5 straight lines and all the straight lines are parallel. Since they are parallel, they have equal slope. So as you can see here, when you compare it with the equation of straight line y equal to mx plus c, we know m is the slope and this c is what? C is when we put x equal to 0, y equal to c. So at x equal to 0, we get y-intercept. So at x equal to 0, we are getting y-intercept. So here the c is varying. So in this case, as you can see here, the y-intercept is 4 and the curve is intercepting y-axis at 4. But for this curve, fx equal to x plus 2, the slope is same. So these two curves are parallel. But since the intercept here is 2, it is intersecting the y-axis at 2. Similarly here, it is x plus 0. So it is intersecting or crossing through 0. It is minus 2. So is intercept is minus 2, x minus 4. So minus 4 is the intercept. So this shows the variation of slope and this shows the variation of intercept. So if you are plotting a straight line, then you can easily know or easily draw a straight line. So now let's plot a few graphs. So the question says plot the graph of y equal to x into x minus 1. So the function is y equal to x into x minus 1. So please try yourselves to plot this graph. And after a few minutes, we will discuss and we will be going step by step and we will be at last we will be plotting the graph. So we'll discuss different steps to plot this graph. So please try to plot this graph on your own. Then we will discuss how to plot this. So let's discuss. So here we want to plot the graph of y equal to x into x minus 1. So first we should see what are the x-intercepts and what are the y-intercepts. So for x-intercept, we need to put y equals to 0. So when we put y equal to 0 equals to x into x minus 1, then x equals to 0 and x equal to 1. So these two are x-intercept. So the function or the graph of x into x minus 1 passes through x equal to 0 and x equal to 1 at x-axis. And then for y-intercept, x equals to 0. So when you put x equal to 0, then y equal to 0. So the graph passes to origin. So x equal to 0, y equal to 0 origin. So the graph passes through origin. So we got a few points. So let's list out the points. We know for x equal to 0, y equal to 0, 1 point we got. And for x equal to 1, y also equal to 0. So we got these 2 points. Now let's see what will happen if the value is between 0. Since we have these 2.0 and 1 and it is tossing both x. Suppose this is the graph we will be drawing. Axis, this is y-axis. 0, 1, 2, 3, 4. Again it is 3, 4. It is 1, 2, 3. And in that side also there will be values. There are 2 points x equal to 0 and x equal to 1 where y equal to 0. So the curve will go through this point and curve will go through this point. So in between the 2 points, whether the curve will go like this, whether the curve will go like this, or whether the curve will go like this, then how we can consider whether it will be concave or convex. Then in that case, we need to find out the first derivative and second derivative. So let's find out the first derivative of the curve. So dy by dx will be x square minus x d by dx of x square minus x. So it will be 2x minus 1. So dy by dx is 2x minus 1. So when you put 2x minus 1 equal to 0, then 2x minus 1 equal to 0, x equal to 1 by 2. So at x equal to 1 by 2, it will change its direction. That is, if it was increasing, then it will be, so it is called as turning point. That is, the direction of the curve changes, and where the curvature changes, that point is known as point of inflection. So this is x equal to half, x equal at x equal to half, the derivative is 0. So the graph, the change is 0 at x equal to half. Then when you calculate double derivative, then it will be d square. Calculating the double derivative, d square y by d square y by dx square. It will be 2. So 2 is positive. So positive means the graph will be concave up. So in between 1 and 2, when we compare at x equal to half, what will be the value of y? at x equal to half, the value of y will be x square minus x. So 1 by 4 minus 1 by 2. So 1 by 4 minus 1 by 2, so it will be minus 1 by 4. So it will be negative. So it will be somewhat lying here. So this is 1, then it will be 1 by 4. Suppose it is here. So this point is here. So the graph will be like this between 1 and 2. Now, since y, suppose, then if you take in other values, like for x equal to 4, then y will be how much? 4 square. Y will be 4 square minus 4. So 16 minus 4 equal to 12. Then at for x equal to 4, y will be 12. So it will increase in this way. So it will go on increasing in this direction. Similarly, when x equals to negative, suppose x equal to minus 2. So when x equal to minus 2 at this point, then y will be 2 plus y will be 4 minus of minus 2 is, so y will be 6. So again y will be in this square. So the curve will be like this. So it will be straight actually, not. So let me see. So when you draw the curve will be like this. Suppose this is x, this is y. So here it is 0, here it is 1. So the curve will be like this. So this is the curve of y equal to x into x minus 1. So this is x axis and this is y axis. And here this point is half, x equal to half and y equal to minus 1 by 4. So it is lying in quadrant 4. Then similarly, plot the graph of y equal to x minus 1 into x minus 2 into x minus 3. So it is similar to that, but there are more number of points where the value of y will be 0 for value of x. So I'll give you 1 or 2 minutes to try this and then I will discuss. So let's discuss this. So now first we will calculate where the value of function is 0 for value of x. So y equal to 0, we have x minus 1 into x minus 2 into x minus 3. So it will be x equal to 1, x equal to 2, and x equal to 3. So we got 3 points where y is 0. So here we write x, here we write y. So at x equal to 1, y equal to 0, x equal to 2, y equal to 0, x equal to 3, y equal to 0. Then in between 1 and 2, we will take a point and say and see whether y is positive or y is negative. So between 1 and 2, suppose it is 1.5. So when it is 1.5, then 1.5 is less than 1. So this will be negative. So this will be positive, but this will be negative. This will be negative. So the product will be positive. So at 1.5, the value will be positive. Suppose at 2.5, similarly at 2.5, the value will be how much? For 2.5, it is positive. It is positive, but it is negative. So there will be one negative. So but 2.5, the value will be negative. Then, so for this point between, so for x less than 2, the value is negative, but for x greater than 2, it is reverse. For x less than 2, the value is positive, but x less than greater than 2, the value is negative. So the function is changing its direction. So at point 2, the function is crossing y. So these are the 5 points we are getting. And again, let's calculate its first derivative and second derivative. So to see where the function is actually changing the direction. But before that, let's calculate the y-intercept. So for y-intercept, we will be putting x equal to 0. So when we put x equal to 0, y is minus 6. So at x equal to 0, y is minus 6. So the point cuts y-axis at minus 6. So we got 1 point here. Now let's take derivative. So when taking derivative, it is dy by dx. Dy by dx will be how much? It will be 3x square minus 12x plus 11. And again, if you take d square y by dx square, then in that it will be 12 minus 12 plus 6x, 6s minus 12. So when you put d square y by x square equal to 0, we will get x equal to 2. So this is the point of inflection, that is the curve changes its concavity at x equal to, so that's why we are getting at less than x. When the value of x is less than 2, d square y by dx square will be positive. The value of x is greater than 2, d square y by dx square will be, that it is different. When x is greater than 2, it will be positive, but it will be negative. So as you can see here, when we put x equal to 3, then it will be 18 minus 12 equal to 6, positive. But when x equal to 1, then it will be 6 minus 12, that is minus 6, so negative. So at x equal to 2, the function is changing its concavity. The function is concave down below 2, but the function is concaving up after 2. So these are the few informations we are getting. So now let's plot the function. So slide. So here now we got, suppose this is x and this is y. Now we find at x equal to 0, y is minus 6. So suppose here this is the point, y is minus 6, this is 0 minus 6. And at x equal to 1, this is 0, this is 1, this is 2, this is 3, 1, 2, 3. All these 3 points, the curve is passing through x-axis. So we will connect this point. sorry, like this, the curve will the point will go like this from this point to this point, and then it will again come to 2. So it will again come to 2. Then it will go to negative, and then it will go to 3 and it will cross 3. And then it will go like this. So this curve will be, it is not actually so smooth in my drawing, but the curve should be smooth. So this will be the curve. So this is y equals to x minus 1 into x minus 2 into x minus 3. So this is the graph of this function. Now there are some other functions. So let's plot these functions also. We know y equal to, it is very simple, y equal to x, y equal to x, y equal to x mod. So for y equal to x mod means this function can written in other form as y equal to x when x greater than 0, y equal to minus x when x less than 0. So when x less than 0, suppose x equal to minus 1, then y will be minus of minus 1, 1. So for both positive and negative values of x, y will be positive. So y equal to x is like this. But since y equal to x mod we are plotting, so it will be both in both these two angles should be same. So y equal to x. So this graph gives us y equal to mod of x. Similarly, y equal to mod of minus x. So y equal to mod of minus x for all the values of x, y will be negative. So here the graph will be like this. This is y-axis. This is y-axis. This is x-axis. So this is x-axis. So this is the graph of y equal to minus mod of x. Then another graph is y equal to mod x minus. So basically this is a shifting function. So when we are shifting the value of y, since we are subtracting here y equal to mod x minus 2, so the graph will be shifting to 2 units down in y-axis. Similarly here in x plus 2, the graph will be shifting 2 orders of the y-axis. So the graph of x equal to, so when you plot the graph of mod x plus 2, then suppose this is y-axis here. This is 1, this is 2. This is 1, 2 like that. So it was y equal to mod x. So when you shift it to this 2, so it will be y equal to mod x plus 2. Similarly, plot y equal to mod x minus 2. So this is y equal to mod x. So when you put mod equals to minus 2, the graph will be like this. So this graph is y equal to mod x minus 2. Again, suppose y equal to x plus 2 mod whole mod and y equal to x minus 2 whole mod. Here you can see initially it was mod x and we shift the value of y because the value of y is shifting. But here as you can see we are shifting the value of x because the whole is mod. So here x is x minus 2 and here x is x plus 2. So here the graph will be shifted in x axis. So if this is y equal to mod x, y equal to mod x, then y equal to mod x minus 2, then the graph will shift in x axis towards positive side, because as you can see when the value of x is less than 1, it will be so where the value of y will be positive in both the cases, but for some value it will be negative. So when you plot it, the variation, so it will be like it is 0, 1, 2. So it will be shifted in this axis. So this is y equal to mod x minus 2. So as you can see here, at x equal to 2, y equal to 0. So when you put x equal to 2, y equal to 0. So at x equal to this curve is y equal to 0. But similarly, when you plot x plus 2 mod, then this is y equal to x mod. But when you put y equal to x plus 2 mod, then when x equal to minus 2, then y will be 0. So at this point, this is minus 2. This is x axis. This is y axis. So the curve will be like this. So this is y equal to x plus 2 mod. So these are some shifting of the curve. Suppose this one value is given. This is mod x, so it will pass to origin. Minus x, it will be different in direction. But when you are shifting the outside the mod function, then the graph will shift in y-axis. But when you including inside the mod, so the value of x is changing, so it will change the function in x-axis, or it will shift. So basically, these functions we did here is called as shifting of the curve. Then now after graph plotting, so there are different types of graphs. Like you can also plot trigonometric graph. You can plot different exponential graph. For example, when you are plotting exponential graph, then so can you tell me for x equal to graph, where the graph will cross y-axis? Suppose we want to plot y equal to e to the power x. For y equal to 0, e to the power x equal to 0. So what will the value of x? The value of x will be minus infinity. So at x equal to minus infinity, it will be y equal to 0. But when x equal to 0, then y equal to e to the power 0 equal to 1. So at x equal to 0, y equal to 1, x equal to infinity, y equal to infinity, x equal to minus infinity, y equal to 0. So when x will be minus infinity, y will be 0. So what will be the function? We got points at x equal to 0, y equal to 1, x equal to infinity, y equal to infinity, x equal to minus infinity, y equal to 0. So what will be the graph? At x equal to 0, y equal to 1. So this is 1, this is 0. X equal to infinity, y will be infinity, and x equal to minus infinity, y will be 0. So this is minus infinity, this is plus infinity. Plus infinity, y will be infinity, but here y will be 0. So it will be like this. So when x is approaching minus infinity, y will approach 0. But when x is approaching plus infinity, y will be approaching infinity also. So here, this is the curve of y equal to exponential x. So this is the curve of exponential function. But similarly, when we plot the graph of y equal to e to the power minus x, then in that case, at x equal to 0, y equal to 1, x equal to minus infinity, y will be infinity, and x equal to plus infinity, y will be 0, because here it is minus sign given. So the nature will be different. So it will be like this. It will cross y and it will decay. So at x equal to plus infinity y will be 0. So this will be like that. So this is y equal to e to the power minus x. So this is the two graph. One is y equal to e to the power x. This is y equal to e to the power x. This is y equal to the power. This is e to the power x and this is e to the power minus x. So these are a few graphs. How to plot them. Then now comes to data calibration. So when you are talking about data calibration, so basically when we are performing an experiment, we are performing experiment with the help of some instrument, but whether that instrument is giving us correct result, how we will know? In order to know whether it is correct or not, we need to first calibrate the instrument. So the calibration is always done in comparison to a known value. For example, suppose you have a watch, but the time of the watch is different. Then how we will say the time is correct? So we will compare this watch to another watch. So by watching the time in the second watch, we will try to adjust the time in the first watch. And when both the watches show the same time, then we can say the watch is showing correct. So calibration is basically the comparison of a measurement value delivered by a device under test with those of a calibration of standard known accuracy. So the standard is the watch which is correct, and the watch which is we are setting the time is the measurement value. So when these two values are equal, then we will be saying that this is calibrated. For example, you must be knowing in ancient times there was no clock, and they were anticipating the time with respect to the position of the sun. When sun is above, generally what happens when sun is above our head, then the time is 12 noon generally, and when sun sets it is 6 p.m. then sun rises it is 6 a.m. So uh, for them the major value is the time, and the calibration standard of known accuracy is the sun. So by knowing the position of the sun, we are calibrating the time and getting the time. So similarly, for example, in case of thermometer, in a thermometer that there is a mercury column, and this mercury column is calibrated. So the height of the mercury column increases as we increase the temperature, or it is sense the temperature. So basically it is based on the principle of thermal expansion, and the mercury column is very small, so it is a property of linear expansion, we can say, because the area portion of the column is very small. So the thermometer is calibrated with respect to the height of the mercury column, and that height is divided into number of divisions, so that shows us the temperature of a substance. Similarly, in case of thermocouple, so we will be discussing it in more details after some time. But thermocouple, what happens in thermocouple, there are two dissimilar wires and they have two junctions. One junction is kept at a temperature or higher temperature, and another junction is kept at a low temperature. So the function which is the end which is kept at a known temperature or lower temperature is known as the reference temperature, and the temperature which is high is called as the measurement temperature. So with respect to the difference between the two temperature, there is an EMF which is induced between the two coils. So from that voltage value we calculate the temperature. So in case of thermocouple, the temperature difference is calculated in terms of the induced voltage. So the thermocouple is calibrated by comparing the temperature difference to the voltage it induces in the voltmeter. Similarly, in case of electromagnet, the magnetic field is obtained by electric current. So the magnetic field, we measure the magnetic field with respect to some, we use generally Gauss meter. Basically, Gauss meter is working in the principle of Hall effect. So when we use a Gauss meter, we measure different magnetic fields, and we to find a particular magnetic field, what amount of current we need to give. So we change the current and we measure the magnetic field. So we calibrate the electromagnet with respect to the current. So in case when we buy an electromagnet, it must be written. So in order to have the magnetic field of strength this, we need to provide some y amount of, suppose we want to produce x magnetic field, we need to give y current passing through it. So these are a few examples of calibration. So now discuss. So let's discuss the calibration technique of thermometer in more details. So in thermometer, we have so here as you can see, one is a measurement value and another is a calibration standard of known accuracy. So we know the ice is at 0 degrees Celsius, it is a international standard, and the boiling point of water is 100 degrees Celsius. So for all the world, the boiling of ice is at 0 degrees Celsius, but boiling water is 100 degrees Celsius. So these are two known numbers. So when you want to make a thermometer, calibrate a thermometer, so bring a simple thermometer without being a mercury column, or fill the mercury in a capillary tube and place that in ice and wait for a few minutes so that the value will be stabilized. Suppose the mercury rises up to this mark. So we mark it as 0 because the temperature of ice is 0. And again, we will be placing, suppose we this same thermometer, we place it in boiling water. So when we place it in boiling water, the value rises to the mercury, the height of the mercury rises and it goes to this value. So this is 100 degrees Celsius. So this is 0 and this is 100 degree. So suppose this is 100 degree. So between 0 to 100, when we divide it equal, when we divide the length, this length into 100 equal divisions, and then one division will give us 1 degree Celsius. So when we go below this 0, 20 divisions, it will give minus 20 degrees Celsius. So like that, this thermometer is scaled or calibrated. Similarly, in case of a thermocouple, what happens? In thermocouple, there is two metals, metal A and metal B. Here you can see those there are two different junctions. One junction is kept at measuring end, or which is used to measure the temperature. Another is kept at known temperature. So when this is, suppose we so the when we connect the voltmeter between these two terminals, then the EMF is induced and we found some voltage, and that voltage we calibrate with respect to temperature. Suppose this is temperature 0 and this is temperature 10. When the temperature 10 is here, the voltmeter is 2.1 millivolt. Then when temperature 20 is here, the voltmeter is 2.5 millivolt. Like that. So we will calibrate the thermocouple. So how the thermocouple works? Suppose there are two junctions, metal A and metal B. As you can see, one junction, these two are at similar temperature, but here these two are at different temperatures. So since there are two different temperatures, here two different metals are used because they have different properties. Suppose it is being heated here, so the electrons, suppose in this metal, the electrons are more, so electron will go to colder side. So electron will flow in this direction. In this case also the electron will flow in this direction, but since the two metals are different, their property will be different. So the field created here, the potential created here, and the potential created here will be different because there will be different rate of flow of electron from this point. So due to the difference between these two, there will be a potential difference created, and this potential difference is due to the difference of the temperature. So these two temperature, cold junction and this measuring junction, we found here. There will suppose this is suppose metal B, electron is flowing more. So there are more electrons here, so it is negative. So electron is flowing less, so there is less electron here, so it is positive. So in between positive and negative, there is a voltage induced, and this is measured with respect to voltmeter. So this is a physical thermocouple, and for an electromagnet, we provide some electric field and we measure the magnetic field here. So it is of 1 point. Suppose so this is a one calibration or relation between magnetic field, but suppose the magnetic field is different at different points. So when we are changing the position, that is, as you can see here, 1, 2, 3, 4, 5, then the value is different. So when you want to find the magnetic field at different directions, then we need to calibrate and draw different graphs. So this basically calibration is used to verify that the instrument is giving the result and the result is correct. So in order to have correct measurement, we need to first calibrate the instrument, because the instrument with time, the performance of the instrument also degrades. So the instrument which we are using, we need to calibrate it with some known quantity within some period of time. Suppose we can fix it whether it will be 6 months, 1 year. So in every year we need to calibrate it again. So now let's solve a few problems based on calibration techniques. So this problem says a pressure transmitter has a calibrated measure of range 200 to 300 psig and an output range of 4 to 20 milliampere. So what is the expected output if the input pressure is 235 pig? So in the question what is given, a pressure transmitter is calibrated. So the pressure for what pressure range it is calibrated? It is calibrated in a pressure range of 200 to 300 psig, and this pressure range corresponds to the so it is calibrated with respect to current value, and this current value changes from 4 to 20 milliampere. So for a pressure of 200 psig, the current is 4 milliampere, and for a pressure of 300 psig, current is 20 milliampere. But when the pressure is 235 psig, then what should the transmitter show? What should be the value of the transmitter? It must be showing, since if it is calibrated in a range of 200 to 300 psig with respect to output range of 4 to 20 milliampere. So you try it, and after a few minutes, I'm giving you a few minutes to try it. Then after a few minutes, we will discuss. So can anyone tell me what will be the answer? discuss this question. So the pressure transmitter is calibrated between the range of pressure which is 200 to 300 and the current range is 4 to 20. So the variation in pressure is how much? 100, and the variation in current is 20 minus 4, 16 milliampere. So when you see in this range, the change in pressure or change in current with respect to change in pressure will be how much? 16 by 100. So it will be 4 by 25. So for 25 change in, it will be for accurate when you calculate 4 by 25, it will be 0.16. 0.16. So yeah, for 1 unit change in pressure, the current is changing 0.16 milliampere per PSIG. So here you can see at 200 it was 4 milliampere. So at 235 what will be the current? So 235 means it has increased 35. So since for 1 PSIG the increase in current is 0.16, for 35 PSIG current will be 0.16 into 35. So 0.16 into 35 will be how much? 5.6. 5.6. So in 35 PSIG current changes 5.6 milliampere, but initially it was for 200 PSIG it was 4 milliampere. So for 235 it will be how much? It is 200 plus 35. So it will correspond to 4 plus 5.6. It will be 9.6 milliampere. So the current output will be 9.6 milliampere. Is there any doubt? Is it clear to you how we are calculating what will be the current? Because here you can see the pressure transmitter is calibrated with respect to current. So the pressure is calibrated with respect to current. When the pressure is varying between a range 200 to 300, the current is changing 4 to 20 milliampere. So 100 unit change in pressure is equivalent to 16 units change in current. So 1 unit change in pressure will be 0.16 milliampere change in current. So the pressure to current change is 0.16 milliampere per PSIG. Since here it is 235 PSIG, so there is 35 units change. So for 35 for 35 units of change, the current change is 35 into 0.16, it is 5.6 milliampere. So initial at 200 it was 4 milliampere. So at 235 it will be 4 plus 5.6, so it will be 9.6 milliampere. Similarly, this is another question. It says a PS transmitter, that's why the pressure transmitter, but here it is a PS transmitter. So in case of PS transmitter, it is calibrated with respect to calibrating the pH with respect to the current. So the range of pH is 5 to 9 pH with a current output of 4 to 20. So what is the pH measurement if the transmitter's output is the transmitter's output is equal to 17.3 milliampere. So it is very similar to the previous question. So let's solve and tell me what is the actual pH value corresponding to 17.3 milliampere. Can anyone tell me what is the answer? Anyone? Similarly, the change in pH, the pH is changing from 5 to 9, that is 4. And the current is changing from 4 to 20, that is 16. So for 1 pH, the current will change 4 milliampere because it is 4 by 16. So 1 by 4 pH or milliampere. But here, as you can see, it is 17.3 milliampere. So 4 is 17.3 milliampere. Initially it was 4. So it is 17.3 minus 4, it is 13.3. So there is 13.3 change in 13.3 milliampere change in current. So we need to find the change in PS, then we will add it to the initial PS. So at 4 it was 5, but 13.3. So the change is 13.3. So it will be 13.3 into 1 by 4 because for 1 change in pH, current change is 4 milliampere. So for 13.3 change in current, it will be 13.3 by 4 change in pH. So it will be 13.3 by 4 is how much? 13.3 by 4. 13.3 by 4 is 3.325. So 3.325, the change is 3.325 because for change of 4, the range is 16. So for change of 3.325, the range is 13.3. So since initially it was 5, so 5 plus 3.325, it will be 8.325. So 8.325 is the pH which corresponds to this pressure of 17.3 milliampere. So initial at 4, it is 5, at 20, it is 9. So at 17.3, the pH is 8.325. Basically, these are linear calibration. That is the pressure and suppose this is pressure and this is current, or this is pH and this is current. It is varying linearly, but the things are different when it is varying non-linearly. So these are all linear calibrations. So the linear linear calibrations are more dependable. So this is another type of question. It says identify the type of instrument calibration error shown in this graph. So as you can see, this is the calibration graph. The calibration graph is obtained input and output. So the actual graph should be the actual graph which it should show is given by this red, but the actual graph which we are getting is given by red, but it should show the graph blue. So as you can see, this graph was passing through 0 origin, but here you can see the graph is not passing through 0. It is not 0 here. So it has some value at y equal to 0. X is not equal to 0. So it has some error here. So the error, so since the question is to identify the instrument and calibration error, so the error here will be 0 error. So is it clear why we are saying it 0 error? Because the ideal graph, it was crossing through 0. But here 0 means it is crossing through origin. But the actual graph we are getting is not passing through origin. So the error associated with the calibration will be 0 error. Another error is, suppose this is a type of error, hysteresis error. Hysteresis error means you must remember there is a hysteresis loop. So when we are increasing the field, it is like that. But when we are decreasing, it will not come in same way. It will come in different way. So when suppose you are giving two calibrations. So the calibration is increasing like that. So when we are increasing the value of X, the output is increasing in this way. So we are going on increasing, but when we are decreasing it, suppose we proceeded in this direction, but when we proceed in this direction, if it comes like this only, then there will be no hysteresis error. But it comes like this, so it came like this. So suppose at this point the value, this was one value, this is other value. So there is some error. This is the error. This type of error is due to hysteresis error. Another is linearity error. Like I was saying, this is a linear relation, but we are getting like this, suppose. Then in this case, the range is equal. Here, the two values are equal, but here, due to the linear relation, the results are different. So in this case, it is called as linear error. So then after that, since we are talking about error, so in next introduction session, we'll discuss about error analysis. Basically, when we are measuring something, then we can estimate up to some extent, and then there is some uncertainty in the measurement. And this uncertainty comes due to different there are different causes of this source of uncertainty. So we'll discuss about error and how the error can be minimized, and we will be solving a few problems related to error analysis, and then we'll proceed towards our basic experiments and the questions related to it. So is there any doubt, or do you have any question regarding the session you want to ask me? Anyone? Yes. I think we should stop here. Thank you all. Good night.